It is part 2 of section 3.23, Polynomial Interpolation Error Theorem. In the first part of the section, we studied polynomial interpolation and constructed interpolating polynomials in the Lagrange form. Here we have a question. When an interpolating polynomial Pn approximates a function f, then what is the error? In this second part, we'll try to answer the question. Let's see this theorem, Polynomial Interpolation Error Theorem. F is continuously differentiable n plus 1 times, and Pn is the interpolating polynomial of degree n of f at n plus 1 distinct points x0 to xn, which are chosen in the interval ab. Then for each x in the interval, there is number psi x. Okay, psi x is a number which depends on x, such that here the difference between f of x and Pn x is given in this way. This is the interpolation error. This theorem can be compared with the Taylor theorem. In Taylor theorem, the Lagrange remainder is given here along with x minus a to the n plus 1. So rather than this product, in Taylor theorem, you'll see here now x minus a to the n plus 1. Right? So it is well compared with the Taylor theorem. Now, for the interpolating polynomial, and we have to make sure this term is small enough, then the polynomial is approximating the function quite well. Let's see here the example. The function f of x is sine x. Now, we'll approximate it by using degree 5 polynomial and equally distributed points, so that there must be 6 points start from minus 1. So xi are here minus 1 and minus 0.26. So each subinterval length is 0.4 because the whole length is now 2. Okay. Now we want to measure the maximum possible error. Okay. So here the points are given, and now following this formula, n is 5, so that we have to get 6 for the derivative, and we measure it, and then this term, but now psi must be between minus 1 to 1, so the maximum possible value is sine 1. Now, we organize this term in x minus minus 1, x minus minus 0.6, so the whole product for that one. Now, by using maple code, we try to measure the absolute maximum, which is this one, so that the difference is now same as that, and this one is bounded by sine 1 and 6 factorial, and this one maximum value is already, we have here g max. So if we multiply these terms, then we can get here 8 times 10 to the minus 5. So once you try to make a fifth order polynomial for sine x between minus 1 to 1, then maximum possible error is this one. This is upper bound. Okay. So it is quite accurate. the polynomial will approximate the function quite nicely. Okay, here we have another theorem for interpolation error. Polynomial interpolation error theorem for equally spaced nodes. Now we'll assume that the points are chosen from A to B equally spaced. So the first we find h, b minus a over n, and then here I is moving from 0 to n and a plus ih, so that here beginning point is x0 a, and the next one is x1, and last one will be xn. Then here the error is bounded by this term. So that when it is equally spaced, then rather than this computation, we may try to use this one to get the upper bound easily. Okay. Here m, capital M, is the maximum of n f to the n plus first derivative, that function, right? Okay. Here, now here we have proof, and you may try to read it, but will not go through the detail for the proof. Okay. Now, for the same problem, same example, with f of x is sine x, now we'll try to get fifth degree polynomial, interpolating polynomial at 6 equally distributed points in -1 to 1. And we try to measure the upper bound by using here practical quantity. Now that one is more convenient, but the upper bound is measured roughly, but it is true. And by using this one, let's try to see the upper bound. In fact, try to measure that one here. Okay, so using Python, we try to get here now, and for f of x, we try to make n plus first time derivative, and for that, now maximum is measured, so n becomes that one. But now, rather than Gmax, we try to use some other parts from the theorem, and we can get the error bound and print out. That is now this one. That is about 1.4 times 10 to the minus 4, which is about twice larger than and more tight upper bound. But along with this a little bit loose upper bound, anyway, it's true. So that the error cannot be larger than this one. Okay. Here, that will be more convenient, but a little bit loose, and so that you have to understand why we are doing these two different upper bounds. Okay. Okay, that's the end of the section. Thank you.